The goals of the lesson. Students will be able to transform the graph horizontally by performing the following transformations: translation, compression and dilation, reflection over the y-axis. Last class you discovered with the Desmos activity, to move a graph left to right, it must be inside the function, and the graph moves opposite the side. So if you notice, here's the activity. This was the original graph, and you moved it 5 units to the right, which meant the function was f of x minus 5, which is opposite what you would think it would be. This is what happens with horizontal translations. This idea with horizontal translations is what is inside the function, you move it the opposite direction of what you think. So you have a minus 2 inside the function, so you would move the graph right 2, which means if you have a point A, you would take the x-coordinate and you would add 2 to the x-coordinate to move the portion of the graph. For all horizontal translations, the y value remains unchanged. Here, this slide represents the other situation. So we have plus 2, which is inside the graph, so we know it moves left or right, and this plus means we're going to move it 2 units to the left. Once again, opposite of what you think. So if your original x-coordinate is A, we're going to take that x-coordinate and we're going to subtract 2. So once again, you take the x-coordinate and you do opposite what's inside, and then you apply that to the x-coordinate. For all horizontal translations, the y-coordinate stays the same. So to reiterate, the big idea, if you have x minus h, that would mean you would move h units to the right. If you had f of x plus h, that would mean you would move h units to the left. When it's inside the function and it's plus or minus, it moves it left or right, and anything inside the function is opposite of what you think. Now we're going to try an example. We are given this graph, which represents f of x. And we're going to take that graph and we're going to transform it f of x minus 4. Because it's minus 4, that means we're going to move all the x-coordinates 4 units to the right. There are 2 ways to do this. You can do this algebraically and you can do this graphically. We'll first start algebraically and we'll do the rest graphically. So given the point -7, -9, we're going to add 4 to the x-coordinate. So we have -7 plus 4, and the y-coordinate is going to remain the same. So our newly transformed coordinate is -3, -9. We can see it down here on the graph. -3, -9. -3, -9. You can see it's moved 4 units to the right. The rest of the coordinates, we're just going to move them by counting. So we have 1, 2, 3, 4. So this new coordinate is +2, 6. 1, -3 goes over 4 units. So 1, 2, 3, 4. So now we have 5, -3. And then 4, -3 goes 1, 2, 3, 4. So the new point is 8, -3. And then 7 goes 1, 2, 3, 4. So our new point is 11, 3. And then we can connect the dots. And you can visually see that our new blue graph is moved 4 units to the right. This example you're going to do mostly on your own, but we're going to start it together. Because it says +6, that means we're going to move the graph 6 units to the left. What you want to do right now with the video is complete this example on your own. Pause the video, answer the questions, and when you go to the next slide, you will see the answer. This example is not actually graphed. So really the only way you can do this example will be algebraically. So if you've done all the other examples graphically, this one you'll need to do algebraically. So we have assume the point -4, 3 is a point on the graph of the function y equals f of x, and determine a point the graphs of the function below. So we have y equals f of x minus 3. So since it says x minus 3, we know the x-coordinate's going to move 3 units to the right. Remember, it's always opposite what you think. So since our original coordinate was -4, 3, we're going to take our x-coordinate and we're going to add 3 to it. Our y-coordinate is going to remain unchanged. So when we add 3 to it, we end up with the new coordinate -1, 3. And that's what happens when you transform -4, 3 and you move it 3 units to the right. Just like before, you're going to complete practice 4 and 5 on your own. Pause the video, complete 4 and 5, answer the questions, and then when you go to the next slide, the answers will be there. We just talked about horizontal translations. Now we're going to talk about horizontal dilations or compressions. Dilation is when our graph gets bigger, and compression is when our graph gets smaller. Both of these are done horizontally, and the horizontal dilation or compression, just like the horizontal translation, is opposite of what you think. So if you have a 2x inside the function, that means it's a horizontal dilation or compression because it's inside the function. Now, because it's a 2, that means you're going to do exactly to the graph opposite of what you think. So you're going to compress it by 2, which means you're going to take your x-coordinate. If your x-coordinate started at A, you're going to divide it by 2. Remember, it was 2x on the inside, and the operation that you're going to perform is you're going to divide all the x-coordinates by 2. Now, just like before, when we were dividing by 2 because it was a 2x, now inside we have f of x divided by 2. So, since it's divided by 2 on the inside, we're going to do the exact opposite operation. So instead of dividing by 2, we're going to multiply by 2. Multiply the x-coordinates by 2. And since we're taking the x-coordinates and multiplying them by 2, we're expanding horizontally, or we're dilating horizontally. So if you take your A, and inside it says divided by 2, you're going to do the exact opposite, which means you're going to multiply by 2. Once again, we're talking about things horizontal. And when we talk about things horizontal, anything inside our function, we do the exact opposite of what's there. So if you have the point A comma B, and with the function, you're going to do s times x. That means inside the function, you're multiplying by s. What does that mean to your actual point? Well, you're going to take that A coordinate, and because it's multiplication on the inside, you're going to divide it by s when you actually perform the operation. And that division by s is going to compress by a factor of s. By that same token, if inside you have f of s, x divided by s, x divided by s. So inside you have division. When you perform that operation to the point, because it's on the inside, you're going to do the exact opposite. So you're going to take s, and instead of dividing, you're going to multiply. And that is a dilation by a factor of s. Once again, anything horizontal, you do exactly opposite the operation with the x-coordinate that is inside the function. Now we're going to do an example. We're going to take this graph and we're going to change it by f of 3x, which means we're going to compress by a factor of 3. Because it's inside the function, we're going to take all of the x-coordinates, and the x-coordinates will be divided by 3. Remember, anything horizontal is opposite what you think. So our original coordinate was -9, -4, which we're going to compress by 3. So we're going to take that -9 and we're going to divide by 3. So our new coordinate is -3, -4. So here's our new coordinate right here. -3, -3, -4. This coordinate up here, we're going to take the -3 and divide by 3. So our x-coordinate becomes -1. So our new coordinate is -1, 4. Down here, we have 3 divided by 3, which is 1. So our new coordinate is 1, -2. Our 6, -2 becomes 6 divided by 3, which is 2. So our new coordinate is 2, -2. And then our 12, 3 becomes 12 divided by 3, which is 4. So our new coordinate is 4, 3. When you connect the dots, you can see that the whole function has been compressed by 3. It's all squished horizontally by a factor of 3. So our new coordinates are, we'll write them all out, -3, -4, -1, 4, 1, -2, 2, -2, and 4, 3. Now you're going to try this one on your own, but we'll start it together. Because it's divided by 2, that means that it's dilated by a factor of 2. And what that means is we're going to take all of the x-coordinates and multiply them by 2. Pause the video and do this to all of the coordinates. On the next slide, you will see the answer to this dilated by a factor of 2. We're going to do this same idea, but we're going to do it with just a single point as opposed to an entire graph. So our given point is -12, 6, and it's on the original function f of x. And we're going to transform that point by taking that and f of x divided by 3. Now because it's divided by 3 on the inside, that means that it is dilated by a factor of 3, which means you're going to take all the x-coordinates, in this case your one x-coordinate, and multiply by 3. You always do the opposite. Since it's divided by 3 on the inside, it's going to be multiplied by 3 on the outside. So our coordinate, which we're going to take, which is -12, 6, we're going to dilate it by a factor of 3. So we're going to take the -12, we're going to multiply it by 3, and we're going to keep the 6 the same. So our new coordinate is negative 36, comma 6. You're now going to do these problems on your own, but I want to talk a little bit about this one. Because there are two transformations, there's both the negative and the 2x. You have to do it exactly opposite of what you think. So since there's a minus, we know we're going to add 5 to the x coordinates. Because it's 2x, we're going to divide all the x coordinates by 2. That means that if you had the original point a comma b, the new point would be a plus 5 divided by 2 comma b. You must first do the translation, so the add 5, then you divide by 2. The answer to this will be on the next slide. Pause the video and try both 9 and 10 before you go to the answer. The last transformation we're going to look at is reflection. So once again, we're dealing with something on the inside. So since there's a negative on the inside, we're going to divide all the x coordinates. We're going to divide all the x coordinates by negative 1. Now, some of you might be thinking, couldn't we just multiply all the x coordinates by negative 1? In fact, we could, except that all of the other operations that we do on the inside of the function are opposite what you think. So when you see a negative x, that should trigger you to do the opposite of negative x, which would this, instead of multiplying by negative 1, divide by negative 1. Now, if you choose to multiply by negative 1 or divide by negative 1, it's the exact same thing. But I like you to think about the fact that anything on the inside is always opposite of what you think. So to get in the habit of dividing by negative 1 instead. So we're just going to do this algebraically. So we have negative 7, negative 6 is part of the original function. And we're going to do negative x. So that means it's going to reflect over the y-axis. And since it's inside the function, we're going to do exactly opposite of what we think. So we're going to divide by negative 1. Negative 1, not negative 7. Negative 1. So since our original point was negative 7 comma negative 6, we're going to take the negative 7 and we're going to divide by negative 1. As always, we keep the y coordinates the same. So when we divide by negative 1, we get negative 7 divided by negative 1, which is positive 7 comma negative 6. So the new point is 7 comma negative 6. You're going to pause the video and do practice 12 and 13 on your own. The answer will be on the next slide. We've now reached the end. The goals of the lesson were to transform the graph horizontally by performing the following transformations: translation, compression and dilation, reflection over the y-axis. If you have any questions, you can go back to the video and watch any parts again. Your homework tonight is homework number 27, a packet that the sub will give to you.